Start where we left off last time. We started talking about systems, and different types of the systems and how we characterize them. Let's continue that path. We talked about what is a linear system. Linear system is a system for which the superposition holds. And we saw that the root of that is in the fact that these systems are described through linear differential equations, or in the case of the analog systems, and the linear difference equations in the case of digital systems. So let's spend a little bit more time on that. Superposition and linear systems. So here's the task that we're going to be faced over and over again in this course and in general in practice. We're going to have a system which usually is going to be linear by design. So we kind of design it so that it has a superposition that holds. We present the system with some input x of t, and the question is, what is an output of this system? This is always the principal question that we are trying to solve. Remember, we actually define the system as an entity or block that performs the mapping between x of t and y of t. So that's our definition of the system. It's through its mapping between x of t and y of t. So there are two ways how we can, in principle, obtain y of t by knowing x of t and the system itself. So let me kind of outline them here, because they will follow us throughout this entire course. And even though it might be a little bit premature here, I'm just going to state them. But I want you to have this big picture here so that you can view what comes later in a proper light. So two approaches for determining y of t. And the first one is time domain. Okay? So we're going to do all the calculations in a time domain. If I were to do this problem in a time domain, here's the approach. And I'm sure a lot of you are already familiar with this, so this is also part of a review. So what I'm going to do is I'm going to present delta of t to this system, and I'm going to observe what comes out in the output. And I'm going to call this, since this is an impulse, I'm going to call this impulse response. So delta of t at the input, x of t is equal to delta of t. And then I'm going to observe what comes out as an impulse response, as a response of this system to this delta of t. We know from the shifting property of the delta function that x of t, now this is x of t, any arbitrary input, then I know that x of t can be seen as an integral when tau goes from minus infinity to plus infinity, x of tau times delta of t minus tau d tau. What you should how you should understand this? Well, look at it this way. Look at per specific time tau. So at that time we have an impulse that is multiplied by the value of the function at that impulse. So you are seeing an input signal as a whole bunch of delta pulses coming one after the other. So if you now see a signal as a whole bunch of delta pulses, then the output is going to be a whole bunch of impulse responses being coming one after the other. Because of the system is linear and the superposition holds, every one of these delta pulses will produce appropriate impulse response. And then your output y of t is going to be integral when tau goes from minus infinity to plus infinity, x of tau times h of t minus tau tau. So again, how do you see that? You decompose an input signal as a whole bunch of delta pulses coming one after the other. Then of course, because the system is linear, every delta pulse will produce an impulse response. And then your output is going to be a whole bunch of impulse responses that are coming all together, and all of them are actually weighted by this x of tau. So let me just put it as a note here. Signal decomposed as sum of a sum of delta pulses. Then your output is a sum of impulse responses. Okay? And that's one way how we can solve that, right? Of course, what is required here is our knowledge of h of t, however we get there, right? If worse comes to worse, we can put the system in the lab, hit it with something that we consider as an impulse, and observe the impulse response. And then what happens, your output is going to be some of these weighted impulses. How do we call this integral here? It's a convolution, right? Your output is a convolution between your input and your impulse response, which when you say that way, it is not really intuitive, but when you understand what this convolution does, it's actually summing all the impulse responses that are coming, by seeing this input signal as a bunch of impulses, then it makes a whole lot of sense. So that's a first approach, and it's called time domain analysis. The second approach is a frequency domain analysis. In this case, you have a system. Instead of presenting a delta pulse to a system, you present exponential, right, over given frequency. And I'm presenting this as a complex exponential. You can present a real exponential and observe what comes at the output. Now, if the system is linear, what can a linear system do to the exponential? It does two things. It will change its magnitude, it will change its phase. When you look at the exponential, there are three components to it. There is its magnitude, its phase, which is 0 here, and what is the third component? Amplitude, phase, what? Amplitude, phase, starts with F. Frequency, right? So there are three things that are complex exponential. One thing that how you recognize the linear system, it does not change frequency. Meaning I put 1000 hertz in, 1000 hertz comes up, right? What changes? It may be louder or it may be quieter, meaning its amplitude, or its phase may change, but the frequency stays the same. So what happens here is I'm going to have that this at the output, so if this is x of t, then y of t is going to be my exponential to begin with, and then times some constant that will change the magnitude, and some angle that will add to the phase. Okay. Now, in general case, both these numbers, this constant that changes magnitude and constant that adds to the phase, will depend on frequency, right? So this h, usually we would write this as a e to the j of 2 pi f t, h of f, magnitude, e to the j, angle of h of f. This h of f, how do we call that? We call that frequency response. Frequency response is much easier to generate for any given linear system. Because here there's a principle. I kind of said, well, you can hit it with an impulse. You cannot hit it with an impulse. What is impulse? How large is impulse? infinitely large. So I kind of said, well, and then you kind of trusted me, and we went over that bridge, right? Because I said, look over there, and you didn't question it. But really, this is very difficult to do. You cannot hit anything with an impulse, because impulse, you can always hit it with something that might approximate impulse. And a lot of times, that may actually damage the thing that you're trying to investigate. So this is more theoretical. But this is very practical. I can present a sinusoidal input to a system. What I'm going to observe is the sinusoidal output of the same system. I can determine the magnitude and phase of the output, magnitude and the phase of the input. I know how much the magnitude changes, which is this magnitude of h of f. And I know how much the system added to the phase, which is this guy here, so I can obtain easily h of f. And then what I do is I do frequencies, what is called frequency sweep. You go change your frequencies and you get pair of points for every given frequency. This way you generate what is referred to as frequency response of a system, right? Now, that means in a lot of circumstances, this is the way how we're going to analyze our system. If I have now frequency response, I can conduct the analysis completely in the frequency domain and in a particular way. So I'm going to take my x of t and I'm going to decompose my x of t as a sum of exponential. As sum of exponentials. How do we do that? Through Fourier analysis, either through Fourier series or through Fourier transform. Essentially, we as electrical engineers, when you see a signal, you really see a whole bunch of sinusoids that arrange themselves to become that signal, right? It's not the signal itself. It is you put the Fourier glasses and you see all these sinusoids that somehow magically align so that you have this pulse train or that you have this particular signal. So in the essence here, we're actually taking x of t, decomposing this into a bunch of exponentials. In this case, we get what we call spectrum of x of t, or which is actually your Fourier transform or Fourier series or whatever it happens to be, depending on what x of t is. Now this one, now if I decompose this as a sum of exponentials, then, and I present it to the system, because the system is linear and the superposition holds, the system was going to look each individual exponential and change its magnitude and change its phase. So you have this whole bunch of sinusoids coming in. Each one of them, as it propagates through the system, will change the magnitude and phase. And then at the end, all of them will add together. So you can sum individual responses. To get your signal y of t, right? So here's where we're standing in a time domain. Here's where we are. This is time, and this is frequency. And many times, I even dare to say majority of times, even though this seems to be a roundabout way of analyzing system, it's actually much more insightful. And this is what we do most of the time. We actually, especially in communications, even control systems, when we try to analyze a system, we look at its frequency response, we take our inputs and we present them as a bunch of sinusoids, and then through this analysis we know exactly what the system does to each one of these sinusoids. And depending on which one do we want to preserve in the output, which one we need to get rid of, we can actually say something about this system here. Both of these analyses are used, right? As a matter of fact, after you determine the frequency response, we can easily go back and determine what the impulse response is. How are these two related? What is H of t?
Multiplication and frequency.
No. Fourier transform, right? The Fourier transform of H of t is h of f. Inverse Fourier transform of h of f is h of t. Right? So if I went and I did frequency sweep and I determined the frequency response of the system by taking the inverse of that frequency response, I can get my impulse response and then use convolution to determine the output of the linear system. So all of these are related, and hopefully by the end of this course you're going to be, not hopefully, you will, by the end of this course you will be, fluent in either a time domain or a frequency domain analysis. Okay, so that was left kind of from the last time about linear systems. Let's talk about the difference between time invariant versus time variant systems. Let's first look at the formal definitions and then give some examples that fit in both of these categories. What is an example of a time variant system? What's an example of a time invariant system? So just a definition here is time invariant is a system whose parameters, which does not change over time. And I kind of remind you again, in our world, the system does not change over time if its impulse response does not change over time, its frequency response does not change over time. So whenever I present them, if I present the same inputs, whenever I present them, I'm going to get the same outputs. In a block diagram kind of way, we can consider this x of t, and let's say I present this impulse to the system, this input to the system, and I get my signal y of t. And I call it here y1 of t. And then let's say I delay this y1 of t, so I get y1 of t minus capital T. In other scenario, I take the same input x of t, and I delay it first, then I get x of t minus capital T, and I present this to a system. Now delayed version of an input, then I'm going to get here y2 of t minus capital T. So if these two are the same, if y1 of t minus capital T is the same as y2 of t minus capital T, the system is time invariant. This is kind of, both of these are a little bit complicated way to say the same thing. The system does not change over time. Its impulse response does not change over time. Its frequency response does not change over time. So if I present an input, particular input, I'm going to get output. If I come tomorrow and present the same input, I'm going to get the same output as I did yesterday, right? So the system does not change over time. Now, what are the examples of such systems? So let's say example 1. Circuits, let's say analog systems, made out of RLC are usually assumed as time invariant. You know, in a purest sense, nothing is time invariant because the only constant thing is a change. So if you come tomorrow, the humidity is not the same, so maybe resistor has a slightly different value. But these are, from practical standpoint, these are the negligible effect. The RLC circuits would, for a long time would act very, very consistent and be almost unchanged. But there are some systems which are inherently time variant. If you look at wireless communication channel, is time varying. Why? Because first of all, there's an element of mobility, right? If I transmit from there and I'm moving over here, then the signal that reaches me always travels different paths and reaches this point in a different way. Therefore, the channel changes itself. Even if I'm sitting still, the environment is in motion, right? So the fact that there's a truck passing by, or the bird flew in between, or there's leaves on the trees that are being moved by wind, all of that will change the properties of the channel. You know, in satellite communications, you have the weather that you're going through. The weather is never constant. So there are some situations in which the system that we're dealing with is inherently time varying. It is still linear, right? Meaning that the sum of the response to the sum of the inputs is going to be sum of the individual responses, but it changes over time. And now we can talk about channels that are slowly changing over time, or even channels that are rapidly changing over time. Usually, time variability is considered as an obstacle, and we have to devise special things to deal with. And there's a whole set of tools that we use to make sure that, especially in the wireless world, to deal with the variability of the channel. Okay, so that's the definition of time variability. Let's look at what do we mean when we say instantaneous versus dynamic system. Instantaneous versus dynamic. Now, generally speaking, the output of the system at the time t will depend on an input to the system at the time t and the past, right? If you look at what that may be not the best example, but if you look at, for example, the stock market, it's Dow Jones Industrial Average, what it is today, it is dependent on what happened today, added to what has happened up to today, all the way, up to the far past. Now, in more practical scenario relative to this course, if you have an RLC circuit, the output of that circuit will depend on what is the energy currently stored in the circuit, and also what is the input presented to the circuit. In general, these kind of systems that have what we call memory are called dynamic systems, right? They are systems with memory. The output at any given time t depends on input at that time, but also of the past trajectory of the system, what has happened to the system prior to that time t. So in general, I guess dynamic systems output depends on output, I should say, at time t. Depends on input x of t and past values, past of the system. How did we get to this point? Majority of the systems are like this, right? We have, certain memory inherent to the systems. There are, however, some systems that we call instantaneous. These are the systems with no memory. In other words, your output at a time t only depends on the value of your input at the time x of t. Now, what is an example of such a system? Let's say you have some sort of network made out of only resistors, right? Then your output at the time t only depends on what is your input of x of t. let's say you're looking at A to D converter, right? A to D converter is specially designed so that the output is only proportional to the sample of the signal at a given time. It depends not on a prior history of that signal, right? So those are the systems that have no memory. You know, there are systems that are, as I say, are specifically designed to be this way. Most of the systems are systems with memory. Now, if you look at it, this is actually the special case of this one. It's just that the memory is 0. Right? So usually, all the equations and all the analysis that we devise for dynamic systems are applicable to these guys as well. Now, causal versus non-causal. These are more interesting, right? In a causal systems, causal system is a system for which output, the output at time t, or time t0, depends on inputs for t smaller or equal to t0. Now this system, you think of this system, it reacts to the inputs, and its output only depends on the past values of the input, right? The alternative to this is a non-causal system. And here, in this case, the output depends at time t0 depends on inputs with inputs for t greater than t0. Now, the first thing when somebody says, well, non-causal is this, then the question is, this is not possible, so if the system is non-causal, it's not real, let's not worry about it. That's not the case. Only the systems that have a requirement to work in a real time are causal systems, right? If something needs to work in real time, you know, at this moment, we don't know how to predict, you know, how to know certainly what the future holds, so we don't really incorporate that into our inputs. But if the system is not required to work real time, there's no restriction, right? And let me give you a couple of examples. There are two important cases, and you know, one of them is a little bit artificially created, and one of them is quite real. So let me look at the first type of non-causal systems. So let's say scenario 1, so non-causal examples of non-causal systems. So here's the scenario 1. And in this scenario, independent variable is not time. Okay, so if the independent variable is not time, let's say it is space, there's no problem in system being non-causal. So here's an example of such system. Consider a system, this is X. There are two charges. This is Q plus, and this is charge Q minus. And I'm looking at response. This is -2, this is -1, 1, and 2. And you can say, well, the electric field is given as Q1, 4 pi or I have them, let's say Q1 and Q2. 4 pi R1 plus Q2, 4 pi R2, epsilon 0, times EX, right? Where EX is this vector here. So you can see here, if I'm looking at the input here, the response at this point, then it depends from the past or prior values. This is R1, and it depends from this one, right? But you can say this is really cheating because, you know, we're not troubled by spatial coordinates because we know that, you know, this is just arbitrary how we set these axes, and it's easily understood that the value of the field at this time depends on something that is, you know, located on this axis, you know, to the right. But there are so there's a next scenario where we create a causal system in a non-real time. And this is a typical, what we call smoothing operation in filtering. You take the input value of the signal, let's say you take 100 samples of the signal, and then you generate the output based on output at the time, let's say, that corresponds to the first sample, utilizing all of these samples that come afterwards. So that's very common in the smoothing applications. If you want to get rid of the noise, if you want to get good compression, then you can use the future samples to obtain the right value of the sample at a given instant. So let me look at an example here of processing of voice in cellular telephony, right? And you can see why is this non-causal system, right? And it's very useful. This happens every time you're taking a phone call. So how is voice signal processed in cellular telephony? Traditionally, this is what happens. We are taking, let's say this is your voice signal. We're taking 20 milliseconds of voice. Right? So this is we sample this and quantize, and we take 20 milliseconds of a sample signal. Now let me just put it in a block diagram. We sample that. How often do we sample voice? What is the sampling frequency?
20 kilohertz.
No?
3 kilohertz.
I can't.
3 kilohertz.
3 kilohertz? No.
2 f-max.
12 kilohertz?
2 f-max. 2
F-max. What is F-max
Uh,
in telephone voice?
8 kilohertz.
8 kilohertz is
2
2 F-max. So we
2
typically sample
4
voice at
kilohertz.
8 kilohertz. And then we perform its quantization. And then what we have here is we actually feed this into a linear predictive encoder. So here's how this works. At this point, you have 8 kilosamples per second. Usually, if you use 13 bits per sample, then you end up here with 104 kilobits per second. And then this linear predictive encoder reduces that through a compression to something on the order 8 kilobits per second. So what happens here is to produce, now think about it, this comes in here, And then what comes output here is another, let's say, package here that is compressed voice, where this is coming at the data rate that is at a smaller rate. But if you look at the output of the system here, at this point, in determining what should be the output of the system at that point, all of these others samples here participate. So you still get 12 milliseconds for 12 milliseconds, 20 milliseconds for 20 milliseconds. But in order to determine what you are going to be sending here, all of these samples that came in this entire 20 millisecond frame participate. So in other words, this sample here contributed to what should be the value of what comes output at this point. So that's a non-causal system. If you try to match this 20 milliseconds to 20 milliseconds, then this one impacted the beginning of this frame. So that's an example of non-causal system. We're not inventing anything earth-shaking. We're not traveling in time or breaking any space-time boundaries here. We're just realizing that if the system is not meant to be real-time, then it can be non-causal. The sample or the output at given time t can depend on the past values of what will be presented as an input. And by doing so, we get a very large compression. You can see you're going from 100 to 8 kilobits per second. There are even coders that are dropping down below, which means we're saving a lot of bandwidth by operating with non-causal systems in this case. All right. Now we talked about also mentioned last time continuous versus discrete time. Systems, and distinction here is kind of the same as the one we had for signals. Systems which process continuous signals are referred to as continuous systems. So let me just put that here. Continuous systems inputs and outputs are continuous signals. Discrete time systems have inputs and outputs are discrete time signals. Okay. Couple of examples. First one is continuous system, right? So continuous system. Your input and your output are going to be continuous signals. Let's look at first order low pass filter. If I present here x of t, I'm going to get y of t. And here, for example, if x of t looks somewhat like this, like a sinusoidal with a lot of noise, then your y of t will get rid of some of that noise. So this may be y of t. Because the low pass filter, the noise is high frequency and it will get rid of it. So this is an example of continuous system. And we've been dealing with these kind of systems all the time. Now, discrete time systems are the ones that are getting more and more, I guess, prevalent. They're pretty much, they're abundant these days. And the little twist here is that discrete time systems are frequently used to process continuous input and output signals. So how is that done? Let me just show you a system that from end to end is continuous system, but inside of its core is discrete time system, so that you can probably on one example see the distinction between the two. And how are they related in some cases. So consider this. So this is example 2. Let's say we have x of t, which is an analog signal. So x of t analog. Then we feed that into analog, or I should say analog to digital, I should say continuous to discrete time. Right? So what happens here? The system is sampled, right? The signal x of t is sampled. So instead of retaining the entire signal, all you do is retain its samples. So at this point, you end up with a whole bunch of discrete values, x of n, where n goes from minus infinity to plus infinity. So you get the samples of the signal. Then at this point, you have your DSP processing, which maps this discrete time signal x of n into yet another discrete time signal y of n, where n goes again from minus infinity to plus infinity. Now, this is also a discrete time signal. And then at the output, you have a conversion discrete to continuous, right? Discrete time to continuous. Okay? And this is my signal y of t. So to kind of illustrate what is happening, let's assume our x of t looks somewhat like this. Right? X of t. Then after sampling, what I end up with is a signal that has all of these samples. Right, so this is my x of n. This is now n. So this now goes into processing. I perform whatever is the processing doing, but let's say it produces something like this. So this is my signal y of n. And this is n. And at the very end here, I get up my pulse back, y of t. So this is, for example, how regenerative circuit might work, or this is the clean up the noise. Let's say this is a noisy pulse. I sample it, I do some filtering on it, and I reconstruct the noise-free pulse. So from this end to this end, I have a continuous time system, right? Right? Because from the input-output of the whole thing, the inputs are analog, the outputs are analog. If I don't look at into the box, I have a continuous time system. But from this end here to this end, I have a discrete time. Okay? So, and this is frequently the case in modern signal processing, modern systems. A lot of them are this way. What allows us to do this is the conversion that happens at this point and this point, and we know this conversion. This is our sampling theorem that allows us to completely preserve the information in x of t by sampling it appropriately, and then here we can reconstruct y of t through proper reconstruction. So you know, here is an example where you have a discrete time and continuous time system in kind of part of a bigger system here. Okay, let me go through a couple of other definitions here. So the next classifications, we have invertible versus non-invertible. Okay. So consider a system for which this is system which we present x of t and we get y of t, right? So we're again looking at this as a mapping. So this system S performs the mapping of x of t into y of t. If there exists a system S minus 1 that performs mapping y of t back to x of t, the system S is invertible. Alternatively, if there is no such system, the system S is non-invertible. Now, let's look at the examples of two such systems. Of two examples, one of an invertible system and the other one of non-invertible. Example one is an invertible system let's say it's a nonlinear amplifier with no memory. So that amplifier will have a characteristic, input-output characteristics that looks like this. This is your input, this is your output. And let's say this amplifier has characteristics that looks like this. So input-output is a nonlinear function of the input, but there is no memory to it. You know, it is instantaneous. If I present this input here, this is what comes at the output, right? So there's a one-to-one mapping there. Now, if you look at, if this is your x of t, then this is your, or x, I should say x, and this is your y. Then an amplifier that's also nonlinear amplifier with memory, but it has the characteristics that might look somewhat like this, is an inverted version of this guy. So here, if this is y, this is x, if you combine these two, you will have an overall transfer characteristics that is input equal to output. We have this kind of systems. This is, for example, in the voice processing, we have A and mu compression. Those are the examples of invertible systems. Or if I compress my signal on a transmission side using this kind of curve, then I would recover this compression or undo this compression if I do this on a transmission. On the reception side, I will undo this compression by running my signal through the inverting function. So together, these two will actually end up with a mapping that maps x of t into x of t. So that's an example of an invertible system. And further, as I said, this is just the general. If you think about A and U compression that we do in the voice processing, that's these are two invertible transforms. Now, if I look at an example 2, this is a non-invertible system. Is non-invertible. That's a rectifier, for example. Another commonly used system that has transfer characteristics that looks like this. If this is x and this is y, then y is x squared. Right? So if you now present x of t, let's say this was my x of t, then the y of t would look like this. And there is really no mapping that would, when you present y of t, that will regenerate back x of t, because you know, the information that this was negative, it was completely lost, right? So this is now x of t, and this dotted line is y of t. And as I said, this system here mapped x of t into y of t, and there is no system that would map y of t back to x of t. So this is an example of a non-invertible system. The last things that, last classification that I want to mention is the stable versus non-stable. And we're just going to mention one criterion of stability. The one that is mentioned in your book. There's a whole big area of control systems for which this concept of stability is a central concept, and they just study a lot of things surrounding stability. But for us here, let's just define it. Stable versus non-stable. And as I said here, we're going to define stability in what is called BIBO, or bound input, bound output. Stability. We're going to say the system is stable if any bound input produces a bound output. Okay? So, for example, if I have a system here, and my input x of t is something that looks like this, then my y of t is, again, something like this, where every time that I present an input for which I can put a bound, the output is also bounded. But alternatively, so this would be stable. But if my system is unstable, there exists an input for which the input is bounded, but all of a sudden you find your y kind of going into becoming larger and larger. Now in practice, nothing can go infinitely large, nothing can be unbounded, but what happens is you present your input and the system starts oscillating, right? So that's your unstable system. You find these systems also kind of common. They have some sort of positive feedback, and they're not always harmful. Sometimes we actually design systems to be unstable. All of our oscillators are designed as an unstable circuitry that kind of oscillates on its own. It doesn't even need to be presented with any sort of.
I'm sorry, Professor.
Uh-huh.
About the oscillation, how do you reduce the oscillation?
Well, how do you reduce it? First of all, you have to decide, is it harmful, right? Some circuits are designed to oscillate. Like if you look at your motherboard, there are oscillators on that board, right?
Right.
So these are the circuits that are designed to oscillate. So in those circuits, you don't suppress oscillations. You kind of make sure that you can precisely control the frequency of those oscillations.
How about if I have
But
a buffer in front of the signals before it oscillates? It will reduce the oscillation.
Well, then if you have an amplifier, right, then oscillations are highly undesirable. And there's like a whole set of tools that you have at your disposal how to reduce oscillations. First, you kind of have to do the analysis to see why does this particular circuit oscillate. Is it the positive feedback? Is it the placement of the poles, zeros, where they are? And then depending on what the causes, you have a whole bunch of stabilizing, procedure. You may add feedback control circuit that prevents from oscillating. You may reduce some gain. You may, do all sorts of things to prevent oscillations, right? So it depends on circumstances. But from our point here, we just have to note that some systems are stable and some systems are stable. Both of them are legitimate. Both of them are described with linear differential equations. Both of them may be linear systems. It relates to, when we later on look at the poles and zeros of the characteristic equation of the system, then we're going to say, okay, if the poles are on the left-hand side, then these systems are stable. If the poles are on the right-hand side, they're unstable. And you will see that we'll go back to this, and we will discover why these systems are unstable, from their differential equations. How you solve that and how you go and compensate for that, that's kind of a different story. But it's a pretty, I would say, long story. There's a lot of stuff there. Okay, so to conclude this, all of this is really, we're still in the introduction part. These first three lectures is just introduction. As you can see, I'm kind of cataloging stuff. I went through types of signals, types of systems. We haven't really tackled any analysis or design so far. We're just saying, okay, you have this, and this is how you define it. You have this, and this is how you define it. As of next lecture, we're going to start really analyzing, and first in the time domain, then in frequency domain. All right, but let me just go to an example of a linear system. And let's see what kind of system this is, and kind of as a preview of where we're headed. And this is your example. One 10 in the textbook. It gives you this system. Have a resistor here. And this is what the C of t, and the output here is really this current, Y of t here, R, L. And it says here, find the relationship that this is the mapping of the system that will take x of t and map that into y. So that's the relationship that we're looking for. It actually gives us some special values here. It says R is equal to 3 ohms, C is equal to 1/2 farads, and L is equal to 1 Henry. So some specific values to help us simplify slightly the equations that we get. So how do I analyze the system? Well, there are some equations that you know from circuit theory. Current through this capacitor, Y of t, is equal to C dVc of t divided by dt. That's the first equation that we have. The second equation that we have, I can say that Y of t is equal to x of t minus the voltage drop here. Well, let me say this. It's equal to L. Well, let me see it like this. Y of t is the current here. So, okay. So the second equation, I'm going ahead of myself, is saying that Vc of t is equal to x of t minus R times Y of t. That's a voltage drop on this resistor here, and minus L d Y of t over dt, which is the voltage drop on the inductor over there. So now, if I substitute 2 into 1, I can I can notate something like this. Y of t is equal c d over dt. And then this whole thing fits in here. So I have x of t minus r y of t minus L dy of t over dt. Okay? So let's tidy this up a little bit. If I bring all the terms that have y on the left-hand side and leave everything that has x on the right-hand side, here's what I have. I have, with the double derivative, I have LC times d squared of y of t over dt squared. And because of the minus, when it goes on the other side, it becomes plus over dt squared. And then if you look at what is with the first derivative, I have rc dy of t on the other side plus rc dy of t over dt. And then plus y of t is equal c dx of t over t. Right, so that's the differential equation that describes this system in general. Now, if I substitute the values, I end up with 1/2, because c is 1/2, L is 1, d squared y of t over dt squared, plus r is 3 times c is 1/2 dy of t over dt, plus y of t is equal to c is 1/2 dx of t over dt. If I multiply everything by 2, you end up with d squared y of t over dt squared plus 3 dy of t over dt plus 2 y of t is equal to dx of t over dt. I didn't make any mistakes, right? Did I make mistakes? Yes, because there was C here, right?
C.
So there was C. No, I didn't. It's fine, right? I'm looking at the notes, but the notes might not be correct. The notes are not correct, right? Because 2 is missing in front of y of t in the notes. So if you look at this system, this is where the starting point of all our discussion. We're going to assume that somebody did this work for us. We're not going to actually be into the modeling part. We're going to say there's a linear system, and in our world this would mean you have differential equation or difference equation that characterize the system. But what we have when we say linear systems, they travel with their difference or differential equation. And this is, in this case, we have a linear differential equation because it's a linear system. It is a time invariant. Why is it time invariant? Because all of our constants associated with this differential equations are constant. It's a causal, right? Because it operates in real time. It is also analog. It is continuous, right? So all of these attributes travel with this system. Now, our objective is going to be this. We're going to be given differential or difference equation, and our objective is going, and we're going to be given an input, and our objective is going to be to solve this differential equation, to obtain the output of the system to an arbitrary. And we're going to examine different ways of how we do these solutions, both in time and frequency domain, both in a discrete time and continuous time. And that's kind of where we're headed. Right? So let me give you some sample problems. Uh, 17-1, -2, -4, -7, and -8. Also, there is, in section 1, one of the big, contains a MATLAB tutorial. It's very good, actually. It's very good. It's a little bit modeled after MATLAB's own tutorial. If you go to the MATLAB website, or if you have a MATLAB, and then you play the tutorial, it kind of follows the same methodology or presentation. But I guess that's how all of us learn MATLAB. We start by saying, okay, let's use it first as a calculator, like with form operations, then let's use it as a scientific calculator, then use it to build functions, and then in no time you're writing complex code that does all sorts of things. So use this section 1, go through that tutorial, it will help you a lot, right? Then you can use it, MATLAB was initially designed to handle all of this kind of stuff, so it's very powerful when it comes to linear system theory. It can help you in your homework, it can help you, it will help you definitely just to know MATLAB on its own. Any questions here? So just to summarize, we kind of went through 3 lectures where I presented what this whole course is about. We talked about signals, how we characterize what kind of signals we have, what are some of the major metrics for the signals and ways of representing them. And then we say, okay, these signals travel through systems, so there are all sorts of different systems, even linear systems, there are all sorts of different linear systems. And then we kind of come to this point where we say, okay, let's analyze linear systems. And we're going to start with looking at the linear systems that are time invariant in a time domain. So that's what it is.